than the other talks I'm going to be giving. This one is going to be a little bit more just trying to give some background and of the ideas that led to the technologies we'll be using in the workshop. And so this is just an overview of my talk. First, I'm going to try to clarify the difference between symbolic AI and machine learning. One thing before I get going, I also want to say, I mean, I'm not sure how this is working, since we're online, but normally when I do talks, I like them to be interactive as much as possible. So if people have questions, I encourage you to interrupt me and ask them as we go. So I'm going to first talk about the difference between symbolic AI and machine learning, just because I think it's important to make sure everyone understands that difference, because machine learning is something that people hear about so much, and a lot of people that I talk to, sometimes when I say AI, they automatically think that just means machine learning, and I just want to clarify the difference fairly quickly. Then I'm going to talk about the history of symbolic AI, and starting with the early work that was done in the field, and then moving on to talk about the first ontologies that were based on formal semantics, and finally wrapping up by talking about the semantic web and knowledge graphs. Okay, so to start with, I just want to clarify the difference between symbolic AI and machine learning. So within AI right now, there's two major approaches, machine learning and symbolic AI. And we're going to be focusing on symbolic AI, but because machine learning is so prevalent in the news and things, I thought it would be useful to just start out and clarify the differences between the two approaches. So machine learning works by having an algorithm process large sets of data called training sets to generate a mathematical model that is the best fit to the test data. Machine learning is typically what people call a black box approach. So it gives you an answer, but it's not that easy to get an explanation as to how the system determined that answer. That's especially true with the kind of machine learning called artificial neural networks, where you'll have things like hidden nodes, and it can be fairly difficult to understand how a particular inference was made. Symbolic AI, on the other hand, is represented by using very high-level languages that represent things like ontologies and rules, and are meant to be highly intuitive to domain experts as well as developers. So this is just the opposite. It's a white box approach, where as people look at the knowledge representation, so the knowledge representation in terms of machine learning is essentially a mathematical model. The knowledge representations in symbolic AI are meant to be constructs that are intuitive to users. And in fact, a lot of the research in symbolic AI went hand in hand with psychological research on how people solve problems, and finding that they use things like taxonomies and rules to solve complex problems. Neither approach is inherently better. They both have advantages and disadvantages. It depends on your problem. It depends on the kind of data. And many of the most advanced AI systems, such as IBM's Watson, use a combination of machine learning and symbolic AI. So I'm just going to give a very simple example of machine learning first. And this example is taken from Andrew Ng's Introduction to Machine Learning class on Coursera. If anyone is interested in learning more about machine learning, I highly recommend Ng's course. It's very good. It's very hands-on. He's a great teacher, and he's he's a professor at Stanford and one of the experts in the field. So a lot of people think about artificial neural networks as being, what machine learning is all about, and that is one technique, but that's only one of many. And so in Ng's class, he starts with this very simple example where we've got a training set of data where we've got the square footage of a house and we've got the price of that house in dollars. And as we look at it, it looks as if it corresponds roughly to a linear model. So we can use a linear regression to find the line, the formula of y equals mx plus b that is the best fit to the training set. We can then use this mathematical model so that when we get a new data point and we want to say we've got a house that's got this much square feet, what would the projected price of that house be? We can use the model and get a prediction that way. Now that contrasts with if we were doing this using rules, we would have rules like if the square footage is less than 1,000, then the resale value is this. And I obviously just made up these rules. With the specifics aren't important. I'm just trying to give the idea. And so this illustrates the difference between knowledge representation in symbolic AI and in machine learning. In machine learning, the knowledge is represented in an equation of the line, or in general, a mathematical model that's not intuitive, to a domain expert. It would be difficult to explain the reasoning to like a real estate agent. In symbolic AI, the knowledge is represented in ontologies and or rules about things like the size of the house. And if you wanted to add to that knowledge by talking to the real estate agent and adding information like the neighborhood that the house is in, the age of the house, things like that, you could develop more rules. Of course, you could also extend the machine learning model in that way, but the way you would extend the machine learning model is not by talking to a domain expert, but by getting more data that includes that kind of data as well, data about neighborhoods, data about age of the house, and so on. So the semantic approach lends itself more easily to explanation and manual adjustment of the model based on domain knowledge, whereas the machine learning approach can be more accurate and is more automated in that you just feed things into the algorithm and it generates the model for you. In this workshop, we're going to be dealing primarily with symbolic AI, and I also want to stress, though, that the integration of the two is a very interesting topic that a lot of people are working on. It's a hard problem, but a very interesting problem. Okay, now that I've clarified and what's at a very high level, I hope, what symbolic AI is, I want to talk about the early history of symbolic AI. So in the very beginning of symbolic AI, people used, especially there were two guys, Alan Newell and Herb Simon, who focused on what were called general problem solvers. So the idea was that you would take any kind of a problem, you would decompose that problem into subproblems, you would solve those subproblems, and then propagate those solutions back up so that you solve the overall general problem. And the knowledge representation used for these general problem solvers were theorem provers that were very close to being implementations of first-order logic. Now, there was a lot of really good results from Newell and Simon's work that are still used to this day. In fact, in my introduction, I mentioned the fact that I worked on the knowledge-based software assistant program for the U.S. Air Force. One of the things we did in that program was we used the ideas from Newell and Simon to provide feedback and guidance to people. So we would have a methodology of software development represented as goals, tasks, and we would know where someone was in that methodology, and we would use that to provide suggestions as to what to do next. So there were important results, very important results from Newell and Simon's work, but there were also some negative results in the sense that having a general problem solver, having what today some people are calling general AI, back then was too difficult. And the other result was that the knowledge representation they were using of trying to use theorem provers that implemented significant parts of first order logic was very powerful, but it only worked on very small problems. In fact, they call them toy problems because they literally, in some cases, were toy problems. One of the classic problems that they worked on was just how to stack blocks on top of each other. So, there were interesting results, but nothing that could really directly scale up into real world use. And this also led to researchers understanding that there's a fundamental trade-off in knowledge representation and reasoning. And in fact, this actually traces back to one of the most important discoveries in mathematics that formed the theoretical foundation for all of computer science. And that was Alan Turing's work on something that was called the Entscheidungsproblem, which is just German for decision problem. So what Turing was working on was trying to find an algorithm such that you could give that algorithm any arbitrary sentence in first order logic, and it would return an answer whether the sentence was valid or invalid. And people thought that such an algorithm probably existed because there was a subset of first order logic called propositional logic that had existed for a long time. And going back to the Greeks, they had an algorithm for determining the validity of any sentence in propositional logic. And first order logic just adds quantification to propositional logic. So people thought that there would be such an algorithm if people could, and if someone could discover it. But what Turing proved, and also Alonzo Church proved the same thing in a different way, but at more or less the exact same time, was that it was impossible to have such an algorithm. So that means that you can never have a language with the full expressive power of first order logic and have an automated reasoner that is guaranteed to finish and guaranteed to return a result. And what this early research in AI did was to sort of extend that finding from Turing to a more general trade-off. That is that the closer you get to first order logic, the more expressive power you have in your language, the harder it is to have a reasoner that works in polynomial time and that will complete in a reasonable amount of time and that can handle non-trivial amounts of data. And these results were summarized in an old but a really important paper, at least in my opinion, by Herman Levesque and Ron Brockman, called A Fundamental Trade-Off in Knowledge Representation and Reasoning. And I just want to emphasize that I have anything that I have a reference for is in the my bibliography, and I also have not just the name of the paper, but a URL. So if you want to follow that and get the paper online directly, you can. And I imagine this paper in particular isn't going to be interesting to a lot of people, but for those of you who are more into kind of the theoretical and mathematical foundations behind artificial intelligence, I think this is a fascinating paper. So this led to the first practical use of symbolic AI, which was rule-based systems. So based on the understanding about the difficulty of using full theorem provers, the researchers, and this was pioneered by people at Stanford, working in the AI lab there and working with the people in the medical center, they scaled back the kind of reasoning they were trying to do considerably. So instead of trying to implement most of first order logic, all they tried to do was to implement if-then rules and use essentially modus ponens. So you have rules like if X is human, then X is mortal, and then you assert a fact like Socrates is human, and then use that rule in modus ponens, you deduce using forward chaining that Socrates is mortal. And so with this very scaled back kind of reasoning, they could develop inference engines that could handle non-trivial problems. Like the first one that they addressed was the problem of diagnosing human blood diseases. And this system was called Mycin, and Mycin led to commercial rule-based system shells for developing expert systems for business. And as was mentioned in my introduction, my first job was a developer at the consulting firm Accenture's AI group to use these expert system shells to develop expert systems in various domains such as finance, government, defense, and manufacturing. And this was not a research group. This was just a part of the consulting firm, just like any other expertise. And we build for our services and worked with clients and developed systems that were used by real users. Now, if you read some of the historical stuff about this first wave of AI, one of the most common memes you'll hear is that this first wave of AI failed because people stopped developing standalone expert systems, and because all the expert system tool vendors were either bought up by other larger vendors or they just went out of business. I have sort of a contrarian view on this, which is my view is that the first wave didn't fail. On the contrary, it succeeded so well that it kind of went mainstream. So for one thing, the idea that people were developing standalone expert systems, at least in my experience, that was never really the case. You would develop a standalone expert system as a prototype or as an academic example, but for real users to field deployed systems, just having a system that was standalone was never any good. What you had to do, and actually the hard part was not developing the rules, but the hard part was integrating the expert systems with the existing other systems like that were developed in COBOL or other languages, integrating them with legacy databases in relational databases. And so the fact that people stopped, didn't develop standalone expert systems was not really a failure, because in my opinion, they were never really doing that in the first place. And in the same manner, if you look at what are called enterprise systems, so there's systems that are called enterprise resource planning, and the biggest one that dominates the IT world these days is SAP. I'm sure people are familiar with enterprise application integration middleware like TIBCO, or document and content management like OpenText, or customer relationship management like Salesforce, or in my day, Siebel, although they've been purchased, I think, by SAP. But my point is that all of these enterprise systems, if you look into them, they have rule-based engines embedded in them. And they're usually to solve specific problems, like, for example, to control workflow over documents in a document management system. But my point is that rules didn't go away. They became mainstream, and they were incorporated into these enterprise systems, and were also part of just a general toolbox that all developers have at their disposal now. Now, at the same time that these things were going on in the business world, there was also progress being made in the development of tools and in the research on expert systems and rule-based shells. And one of the first developments was the extension of rule-based systems with the addition of taxonomies or ontologies, essentially, class models such as dog is a kind of mammal, and mammal is a kind of animal, and Fido is an instance of dog. It was soon apparent that it was useful to have these kind of models available for the rules to interact with, because when people looked at the rules that were written in the very earliest expert systems, they found that a lot of what they were doing was to do this kind of classification, only without actually having a model written down, but just for sort of the model was implicit within the rules. And that making the model explicit, making a taxonomy or ontology explicit, made made it much more intuitive to develop the systems and to write the rules, and it also made them much more efficient than having the ontology embedded inside of the rules. Now, these first ontologies and taxonomies that were included within rule-based systems were ad hoc. By that, I mean there were guidelines, so there would be methodologies that says, here's when you make one thing a subclass of another thing. But these rules and guidelines were never represented explicitly in the system. They were not enforced or reasoned about. They were just there, and people often didn't use the hierarchies correctly, actually. And so people realized that it would be good to have a language where you explicitly represented what it meant for one class to be a subclass of another, or for an object, an instance, to be an instance of a certain class. And the first language to have a formal semantics for an ontology was called KL1, and that was developed by Ron Brockman, who was the same guy who wrote that paper that I mentioned earlier on the trade-off between knowledge representation and reasoning. So now I'm going to talk about that work of developing ontologies based on formal semantics. So the language that Brockman created, it was called KL1, and it was the first ontology language that had a reasoner. And rather than have an inference engine the way rule-based systems did, which did forward and or backward chaining on the rules, KL1 had a classifier, which was a kind of theorem prover. And the classifier took as input various descriptions about classes, their properties, and things like that. And then it inferred the actual ontology from the descriptions. And one of the results from this kind of research was people found that the classifier could actually be used very much the way an inference engine was used in a rule-based system, solving various kinds of problems. So for example, determining that a diagnosis is equivalent to determining where a taxonomy, where a disease falls in a or where someone's symptoms fall within a taxonomy of diseases. And there's an interesting paper about this written by a guy named Bob McGregor, who is someone I worked with at the Information Sciences Institute. So the next stage in the symbolic AI and knowledge representation was something called the Darpa Knowledge Sharing Initiative. So in the late 80s and early 90s, the US Defense Advanced Research Projects Agency, or DARPA, funded this research program. And as I don't know if people probably know that DARPA funds the majority of advanced computer science research in the United States. They, as I'm sure most people know, they funded the ARPANET. They created the ARPANET, which eventually morphed into the internet. And they funded a lot of other research in computer science areas. And the knowledge sharing initiative was funded by DARPA, partly based on the success of object-oriented programming was having in US industry. So this part of the success of object-oriented programming was the idea of software reuse. Because object-oriented programs were defined in terms of domain objects that modeled the real world, it was easier to find and reuse object-oriented models than it was traditional structured code. However, it was still harder than people thought it should have been, because even though object-oriented programs are still represented in hierarchies that model the world, they are still code. So they're at a very low level of abstraction, and they're obviously tied to one specific programming language and can't be reused across multiple different languages. So the goal of the knowledge sharing initiative was to find ways to get beyond these restrictions of object-oriented programming and to facilitate reuse at the level of knowledge as opposed to at the level of code. And this resulted in several different languages being developed. I'm only mentioning two here, but there are several more. One of them was called the Knowledge Integration Framework, or KIF, and another one was called Loom. And Loom was one of the direct successors to KL1. And it was a language that had a classifier. And I worked at ISI using Loom to build business-to-business applications between the Department of Defense and there's a lot of defense contractors in Southern California, which is where ISI is. It's near Los Angeles. And so the person that I worked for, Bob Netchis, was a big believer in having us develop real world systems to actually test out the ideas. And the domain that we settled on was business to business negotiation between the Department of Defense and various vendors in Southern California. One of the important differences that came out in this stage of the research was the difference between frames and objects. So in most of the knowledge sharing initiative, those languages use the term frames. In object-oriented programming, they use the term objects. There really isn't that big of a difference between the two, but the main difference is kind of the emphasis of the communities that they came out of. Frames came out of a community that was interested in psychology, in the way people thought, and based on research by people like Roger Schenck, who looked at even very simple problems like when someone goes into a restaurant, what are the things that they know how to do? The idea was that certain stereotypical kinds of situations, such as going into a restaurant, trigger a script or a frame that provides a context, and that then by filling in certain values in the frame, you can then create a solution to specific versions of that problem. And as a result, frames were a very eclectic and heterogeneous kind of knowledge representation. They were very flexible and had all kinds of different paradigms. So triggers that were triggered when you set or got the value of a property, methods, of course, rules, and there were also facets on the values of properties in frames. So you could annotate a particular value with additional metadata, which is called a facet. Whereas object-oriented programming came more out of the software engineering community, and they were concerned more with data encapsulation. And whereas in frames, you tended to expose the data, in object-oriented programming, the idea was to hide the data. And the thought was, which I think turned out to be very valid, that in so doing, by hiding the data, by only allowing people to access an object through well-defined interfaces and not directly access the data, you made reuse much more possible, because you could reuse something without needing to understand the details of it, and without having the capability of possibly messing up the internal details of it. So as a result, most people now use the term objects rather than frames, although if you look at some of the papers like in my bibliography or about this earlier research, you'll see the term frame come up a lot. But for the most part, they're very similar. And from this point on, we will be using the term objects rather than frames. So finally, I want to finish up and talk about the semantic web and knowledge graphs. So in 2001, Tim Berners-Lee, who, as I'm sure everyone knows, is one of the inventors of the internet, he wrote a seminal paper published in Scientific American where he described the need for a semantic web. And in that paper, he said that the ideal that he and other people had in mind when they first created the internet was always to make it a semantic web. But the technology that was available at that time didn't make semantics as part of the internet feasible. So instead, they compromised. They compromised on HTML, which was a language to represent the structure of documents and linkage between one document and another, but there was actually no semantics as to what the document was about or what a link between two documents might mean. So utilizing results from the Darpa knowledge sharing initiative, the W3C, which is the organization that manages other internet standards such as HTML and HTTP, they came up with a standard called the Web Ontology Language, or OWL, which is designed to provide that semantic layer underneath the internet. Now, when Lee first published his paper, and when OWL first came out, and the early versions of Protege, I've been using Protege for quite some time, and I remember I was kind of surprised that people in industry weren't as excited about OWL and Protege as I was. And as I thought about it, I realized that the reason was that at that time in the early 2000s, so much of the advanced work in the IT world, at least in the United States, I think it was different in Europe and outside the US, but especially in the US in the early 2000s, so much of it was dominated by machine learning that people didn't pay much attention to the semantic web at first. But in the last decade, large corporations that are very influential in terms of how businesses see their IT world, and specifically Google, Facebook, and Amazon, have all embraced the technology in a really big way. Now, the thing is, when they talk about the technology, they usually use the term knowledge graphs, but if you actually look at the technology that they use, it's for the most part the exact same technology as the semantic web. It's just in the business world, at least in my experience, they tend to call it knowledge graphs, whereas we tend to use, in the academic world, we tend to use the term semantic web, but it's more or less the same technologies. And I think there will be other talks later on in the workshop that get into the specifics of knowledge graphs. And I have a couple of papers in my bibliography that give an overview of some of the real world, large-scale applications that the technology is being applied to now. In Lee's original paper, he had a picture like this, which was a vision for the semantic web stack architecture. It's kind of a traditional stack architecture where you have the lower level things in the bottom. So the things that define graphs like XML, RDF, and RDFS are the foundation. The things that provide semantics are the web ontology language and the rules. And then you have things like cryptography going up, vertically across the entire stack. So that was the vision, and now the vision is now reality. So this is the stack that we'll be primarily utilizing within the workshop. We're going to be using RDF and RDFS as the foundation, the web ontology language for semantics. For the reasoner, we're going to be primarily using the palette reasoner. For rules, we'll be using the semantic web rule language, and there's going to be talks on all of these boxes in later parts of the workshop. And Sparkle is a query language, and Shackle is for constraints. And then on top of the OWL, we have reusable vocabularies like friend of a friend and Dublin core for metadata. So these provide reusable vocabularies to standardize the way we refer to certain things across all the different domain ontologies. And then finally, at the very top, we have ontologies designed to solve specific problems. And three that we'll use the most, or reference the most in this workshop, are the pizza ontology, which is developed for the tutorial on Protege, the Into ontology developed by Biswanath and his team for representing information about academic institutions. And I'll also talk a little bit about the Kodo ontology that Biswanath and I have been developing for data about COVID-19. And so I just want to wrap up by saying that essentially what I think of the semantic web and knowledge representation in general are all about, it kind of comes down to what's known as the DIKW pyramid, where you take data at the very foundation. You've got lots and lots of data, and you add more and more higher levels of metadata, abstractions, knowledge, rules, ontologies, etc., until eventually you go from data all the way up to wisdom. And I mean, in my opinion, that's the core idea behind knowledge representation and behind the semantic web. Okay, thank you. Are there, and here's the bibliography with URLs if people are interested.
Thank you very much.